Right. So this is the Lendava pilot. In Lendava, we have two heat sources. On one side, there is a geothermal source, and we also have a backup source in an oil boiler. We have two heat tanks. The energy from the geothermal source is sent to the is stored in these heat tanks, and if it is needed, then this energy is provided to the consumers. Each of these heat source has a capacity of 1,000 liters, and they are filled with water and also with phase change material. We stratified the tanks by height in 4 layers. Each layer has the same volume, same mass, but they have different surfaces. The bottom layer and the bottom layer and the layer in the top has a bigger surface than the layers in the middle. We also modeled the effects in these layers, like buoyancy effect, flow direction, conduction of heat transfer, and convection. I will show you the equation for water in the layer number 2. For example, this is the equation. So the temperature of water in layer number 2, its differential is depends on its own temperature, also on the temperatures of neighbor layers, T1 and here's T3, and it also depends on temperature of outside air and the temperature of the phase change material. We have here some flows, Q12 and Q21. This is the flow through the tank, and one of these two flows is always 0. This is because the flow at each moment can go either up or down, and it's actually a difference between the flow that come in the tank from the geothermal side and the flow that goes to the consumers, the flow demand. We also have a lot of parameters here, like coefficients of heat exchange. These are KC, KB, and H parameters. We found that parameters and calculated them from the table of materials. But also, if we have a measurements of temperatures, then we could calculate it from them, and there would be more precise. As I said, in the tank, we have beside the water, we also have a phase change material. In this situation, we use ATS 50. It change its phase on 50 degrees Celsius, and we modeled each layer with 2 variables of PCM material. One variable is temperature of it, and the other is latent energy. So latent energy is energy that is needed for this whole material to change a phase from solid to liquid. The good thing here is that this material absorbs and release large quantities of thermal energy at constant temperatures. So, for example, if this material cools down, they will release energy, and when its temperature reaches 50 degrees, they will still releasing energy while staying at the constant temperature at 50 degrees. so that that will keep the tank warm. So there are two energy sources. One of them is a geothermal source. In geothermal source, we calculate the power that it provides to the heat tank. That power depends on a flow, which can be from zero, in range from 0 to 6 cubic meters per hour. And also it depends on a difference between the temperature of geothermal source and the temperature of water in the return pipe from the heat tank. The power of the heat exchanger can goes from 0 to 70 kilowatts, and this is the price that we need to pay for 1 kilowatt hour of energy. The other one is oil boiler. We can see that price for energy from oil boiler is about 4 times bigger than the energy we pay for the geothermal side. So we will use this oil boiler only when it is necessary. When it is turned on, the minimum power of oil boiler is 71 kilowatt, and this is the range for its power. So we also control this valve here. It is open always when the boiler is turned on, but also when the boiler is turned off and the supply temperature from the boiler is higher than the return temperature to the boiler, then this valve will also be open. That's because even if the boiler is turned off, but it still has some energy, we want to use that energy. And the control for this site is very similar to one that Philip describes for lights. We also need a power demand profile for a day, flow demand, outside temperatures, geothermal supply temperatures, and the user can choose what will be the minimum temperature for supply medium from heat tanks. And the result of the optimization will be the optimal schedule of heat sources and their powers, so the user will know at what time day to turn on a boiler or to turn off, and when to switch a valve open and when to switch it closed, and also what powers of geothermal site and what power from all boiler is needed. So that's the model, and now if you have some questions.
The outside temperature here is it's not the temperature of the somewhere outside, it's a surrounding in this
yes,
in the space where the storage is located, right?
It's about room. It's a room temperature, about maybe.
Yeah.
20,
okay.
20,
okay. Thank you, Philip. I want just to add that for about 1 week we are now testing the system, and first recognition is that till -5 outside temperature, the system does not need a backup. So this is for us a good sign that we are on the right way, that we don't use any more fossil fuel for this system. And the second remark is just the price that you mentioned before. It is a general price now for district heating from geothermal, from petrol side of the distributor. But after they will sign a contract, Yes, this. They probably gonna be some modification based on the surface and the buyer and so on, but it's a general price.
Okay.
I will send you when the contract is finished, then it's gonna be a fixed price for that.
Okay, great. Thank you.
Also, just to mention, this price can be added as a parameter in the Excel document, so the operator can change this price.
Of course.
If it changes sometime.
And the very important thing, I think, for this geothermal source is since we figured out that it's not, let's say, a constant supply, but there is a time in a day where you have a possibility to draw more, and then you maybe have a time of the day where the supply temperature in the geothermal source is too low. It is very important for the optimization to presume this temperature profile available on the primary site, because that's what then gives you the advantage in predictive control to take out the energy when it's available, and then for instance you would be able to survive even for lower temperatures than -5, you know, because you would pump in advance your storage and then figure out how not to use the oil boiler. So the availability of this temperature, so the temperature profile of the primary side would be very good to know, actually, as a, let's say, as a prediction when you can draw the energy from the network and when you cannot.